Hello, welcome to Maths with EJD. We continue to talk about probability in this video, and today the focus is on probability rules. Probability rules. And of course, we'll start first of all with probability axioms. Probability axioms. Okay. Um, the probability of an event is a measure of the likelihood. We talked about this in the first video. The measure of the likelihood that the event will occur. That the event will occur. The three basic axioms of probability as proposed by Andrei Kolmogorov form the foundation of probability theory. Okay, so business is to check out the axioms. The first axiom is the non-negativity axiom. Non-negativity axiom. Okay, so and this is that the probability of any event A is always non-negative. It's always non-negative. In the introductory video, we saw that the least probability is 0 when it is certain that something is not going to happen, and the highest is 1 when it is certain that the thing will happen. Every other thing is in between 0 and 1. So non-negativity is guaranteed. So the probability of any event A is always non-negative. That is, probability of an event A happening is always greater than or equal to 0. It is always greater than or equal to 0. Okay. So no matter how hard you try, the probability goes outside of this range. So the probability, for example, the probability of rolling a 4 on a fair six-sided die is 1 out of 6 because there's only one possibility of getting a 4 out of all the possibilities. So, and this is all. So this 1/6 is a non-negative number, which is a non-negative number. No matter what you do, the probability of any event will always be positive. It can be less than 0. Okay. Then we have the second axiom, which is the second axiom is the normalization axiom. Normalization axiom. So the probability of a certain event of course the sample space S is of course 1. So the probability of a certain event is 1. So if you look at the probability of a certain event with the sample space S is actually 1, meaning that probability of the whole sample space is actually 1. That's the normalization axiom. Example, if we toss a coin, the probability of either getting a head or a tail is 1. So that's the probability of getting a head plus probability of getting a tail is 1. Since these are the only two possible outcomes, So that simply means that the probability of the whole sample space is always 1. Okay. And of course, that results to, then we go to the third one, that is the third axiom, which is the additivity axiom. Additivity axiom. So if two events, A and B, are mutually exclusive. Mutual exclusivity simply means that the events cannot happen at the same time, or that they cannot overlap, cannot happen at the same time. So the probability of either A or B happening is the sum of their individual probabilities. This actually applies to the previous example of the sample space, right? So probability of getting a head when you toss a coin is 1/2. Probability of getting a tail when you toss a coin is 1/2. So probability of getting either a head or a tail is the sum of probability of getting a head plus probability of getting a tail. And that gives you that one that we see in the sample space. So that kind of thing applies here. So we're saying that probability A union B is the same thing as probability A. This is like probability A or B, so to speak. So that's probability A plus probability B. And this happens if A intersection B is empty. We've done set theory before now, so you can refer to the playlist so you can understand what this whole empty set thing is about. Okay, so for example, you have this when rolling a fair. It's always important to say whether it's fair or not, because in the second video I talked about a fair die and an unfair die. So when rolling a fair six-sided die, the probability of getting a 1 or a 2 is probability of getting a 1 plus probability of getting a 2. So probability of getting a 1 is 1/6, because there's only one out of all the 6 possibilities. And probability of getting a 2 is also 1/6, meaning that you have 2/6 altogether, which is equal to 1/3. So, of course, this is happening because these two events, that's one occurring or two occurring, as these two events cannot occur simultaneously. So these are the three simultaneously. So those are the three axioms of probability. So we have the non-negativity axiom, no probability can be negative. We have the normalization axiom. That means if you put all the sample space together, that's 1. So if you put the first axiom and the second axiom together, that's where you have the idea that probability cannot go below 0 or go above 1. Okay. So probability of A, so to speak, probability of A is always less than or equal to 1. then greater than or equal to 0. So the probability of an event happening actually lies between 0 and 1. That's what that simply tells us. Okay, and then we have the additivity axiom. So for mutually exclusive events, the probability of their sum is the sum of their individual probabilities. Okay, so let's go to addition rule. There's something like addition rule, since we're talking about probability rule. So we've talked about the axioms. So let's talk about the addition rule. So the addition rule is used to calculate, it is used to calculate the probability that one of two events will occur. So that is the idea of or. So the rule depends on whether the events are mutually exclusive or not. So we just saw a very good example of mutual exclusivity, but now this is driving it home better. So the addition rule depends on whether the events are mutually exclusive or not. Okay. So let's check first of all let's check for mutually exclusive events and see what happens. Mutually exclusive events, just like a repetition of what we did previously. So for mutually exclusive events, okay, we have that two events, A and B, are mutually exclusive, if they cannot occur, at the same time, or you can say if they do not overlap, like I said earlier. So in that case, the addition rule was what we saw before, but better state. Okay, yeah, we've saw this before already, right? So the addition rule for mutually exclusive events, in that case, will simply be probability A union B, which is equal to probability A or B, like I like to say, is the same thing as probability of A plus probability of B. Since A and B do not have anything in common, so that's like you have A happening and you have B happening. You have A happening here and you have B happening separately. So you have this and they don't have anything in common. That is mutually exclusive events. Okay. So, and a very good example of that will be this, that if we consider drawing a card from a standard deck of cards. So the probability of drawing a king or a queen is, now in this case, you see, you have distinct cards for kings and distinct cards for queens. So you don't have a king-queen card, right? That's why the event in that case is mutually exclusive. So it's like probability king or queen is equal to probability king plus probability queen, because there are no cards that contain the two. So in that case now, there are 4 kings, right? So you have 4 kings out of 52 cards plus 4 queens out of 52 cards. Altogether, you have 8 over 52, and that is equal to 4 in 8 is 2, 4 in 52 is 13. So the probability of drawing either a king or a queen will be 2 over 13. Okay? That's the possibility of drawing either a king or a queen. So that's for mutually exclusive events. So when we talk about the next one, which is non-mutually exclusive events, non-mutually exclusive events. So for non-mutually exclusive events, so we say two events, A and B, are non-mutually exclusive if they can occur, simultaneously, or they can overlap, right? They can occur simultaneously or they can overlap. So in that case, the addition rule for non-mutually exclusive events is probability A or B, either A or B, but because A and B have something in common, so that's probability A union B, and that is equal to probability A plus probability B minus the intersection between them to remove that repetition. So you have, this is A, this is B, like this. So, and then they have this region in common. So you have, so the probability that the whole of A is happening contains this region. This is it here. And then the probability that the whole of B is happening is everything here. So A contains the region and B contains the region. So for you to remove that repetition of regions, right, then you have to subtract this. Under set theory, I made different diagrams to show each region, and this shaded region is actually this part now. So you have to subtract that part to avoid it repeated twice, because it is part of A, it is part of B, and then you have to remove it. But in the other case, right, there's no common region. That's why we just add these two and we are good to go. All right. So that is for non-mutually exclusive events. So let's try to drive that point home. And so for example now we have this. Suppose we draw a card from a deck. So the probability of drawing a red card, or a king is, now there are some red cards that are king cards, right? So in that case now we have, okay, well, before we even start talking, so we can say we need to know, okay, well, because of the overlaps, right? We know that the probability red or king is equal to probability red plus probability king minus probability red and king, red intersection king. That means that there are some cards that are red kings, right? So now this is because there are 26 red cards. There are 26 red cards and four kings in the deck, right? But two of these kings are red. So you have king of hearts and king of diamonds Okay. So in that case, we have the following probability that you're going to have a red king is 26 over 50. You're going to have a red card rather is 26 over 52. Then probability that you're going to have a king is actually, there are 4 kings altogether. That's 4 over 52. But then what about probability of having a red king, a king that is red intersection king? That is actually 2 over 52, like we said. Okay. In that case, we say so probability red union king is equal to probability red plus probability king minus probability red intersection king, that is red and king together. So in that case, we have probability red, which is 26 over 52. Probability king is 4 over 52, while probability red and king together is 2 over 52. And putting all that together, we have 26. That's 20. So this is 26 plus 4, 30. 30 minus 2, that's 28 over 52. So 4 goes in 28 7 times, 4 goes in 52 13 times. So the probability of drawing a red or king is actually 7 over 13 because we have 2 cards that are both red and king, while we have 26 that are red, while 4 are king. So that concludes the addition rule. So addition rule has to be considered for both mutually exclusive events and non-mutually exclusive events. Okay, so let's move on to multiplication rule. Multiplication rule. That's the third key aspect. Multiplication rule. So the multiplication rule is used to calculate the probability of both events A and B occurring together. Okay, so in this case, we have to consider both independent events and dependent events. So let's start with independent events. So for independent events, we say that two events are, two events A and B are independent if the occurrence let me write that better. If the occurrence of one does not affect the other. So the multiplication rule, in that case, the multiplication rule for independent events is probability A intersection B is equal to probability of A multiplied by probability of B, because one does not affect the other. There's no overlapping, so to speak. And then we talk about an example in that regard. And so consider flipping a coin. You flip a coin and rolling a die. Flipping a coin and rolling a die. So the probability of getting a head, you are flipping a coin and you're rolling a die at the same time. So the probability of getting a head on the coin and a 3 on the a 3, right, on the die is this. It's calculated as follows. Probability head intersection 3, the head in the first place does not affect 3 in any way because they are totally different. So of course, if you roll a die, you get head or tail. If you toss a coin, you get 1, 2, 3, 4, 5, or 6. So probability of getting a head, that's 1/2 here. Probability of getting a 3, that is 1/6 here. So the probability of getting a head and a die, a 3 together, that's probability head multiplied by probability 3. So that's probability head 1/2, probability 3 1/6. So everything becomes 1/12. That's for independent events. So now let's talk about dependent events. So under multiplication rule, now let's talk about dependent events. So two events, A and B, are dependent if the occurrence of one event affects the occurrence of the other. So in this case, the multiplication rule for dependent events is probability A intersection B equals probability A multiplied by probability of B, given that A had happened. Okay, so in this case, we are talking about dependent events. So if you, after carrying out the first experiment or something, so the next experiment is going to be dependent on the first one you had carried out. So here now we have a condition. So we say where probability B given A is the conditional probability of B occurring given that A has occurred. Okay. So for example, suppose there are 3 red balls. There are 3 red balls and 2 blue balls in a bag. If one ball is drawn and then another ball and then another ball is drawn without replacement, without replacement. Okay, the probability of drawing a red ball first and a blue ball second is, okay, you have probability red first times probability blue second, given that red had been drawn first, given red first. So that is, of course, you have 3 red, 2 blue, right? So you have 3 red, 2 blue. Okay. So at first, that's a total of 5 balls altogether. So if you draw red first, so when you draw that red, it's 3 out of 5. That's 3/5 multiplied by the time you draw 1 out of the red. So you have 2 reds remaining, so that you now have a total of 4 balls remaining. So by the time you're drawing the blue now, so it means you're going to have 2 blue balls out of a total of 4, right? So that by the time you do put all of that together, that'll be 3 times 2, 6 all over 20, and that is 3/10, or if you like, 0.3. So the probability that you get a red first, blue second would simply be 6/20, or 3/10, or 0.3. So these rules actually form the basis for solving more complex probability problems in various fields such as statistics, engineering, data science, and the rest of them. Now, before we go, I like to expatiate on, this on dependent variables, right? Independent event, that is. So imagine that, okay, guess I want to just let me go totally say, okay, this now. So, with the 3 red, 3 red and 2 blue, right? 3 red and 2 blue. So, so you can have this question. 1, what is the probability? Let me just shorten it. Probability 2 different balls. 2 different balls, right? I mean, or 2 different colors. I think that's a better way to look at it. Probability that you're going to draw 2 different colors from the bag. So in this case, now it means the probability can be that red is first and blue is second, or blue is first and red is second. That's really important. So that's red first, blue second, or blue first, red second. That's what 2 different colors can mean. So that means you have the probability red first, blue second, plus probability blue first, red second. So in that case, you have, of course, so each case has to start with a fresh sampling. So when you do the first one, right, you have 3 red out of 5, and then you have 2 blue out of 4. So that's the first one. But if it is blue first, okay, if it is blue first, what do you have? You have 2 out of 5. So after each situation has to start afresh. So once you have plus, you start afresh. 2 blue out of 5 total times 3 red out of 4 remaining after you have drawn the first blue. Okay, so here you have 6/20 plus 6/20 again. So that is without replacement now, without replacement. Okay, so that will give you 12/20, which is 4 into 12, that's 3/10. Still like what we had before. Okay, so this is now without replacement. So if we have this without replacement without, okay, or let me do it this way. Okay, let me just say without replacement up here, without replacement. But what if you draw the ball with replacement? Okay, so you have it with replacement. That means you just see the ball and you return it. So with replacement would simply be with replacement. So that would simply be something like this. It would be that you have, okay, of course, everything is the same up to this point. But then by the time you start implementing, it's like, since it's with replacements, you have your 3/5. You put it back, so you get 2/5 plus blue now 2/5 times 3/5. With replacement, the number of balls never change. So you have 6/20. I mean 6/25 now. So here the chances are less. So 6/20 plus 6/20, 6/25 plus 6/25. That's actually 12/25. So now the chances are higher. I mean, the chances are less rather, because you have 12 possibilities out of 25. If you replace the balls. Okay. So again, can we still talk about that? Can we still extend that? Okay, you have three red, two blue. So you have 3 red balls, 2 blue balls. So the question now is, what is the probability? What is the probability that you have same color? So that the two same color when you draw 2. All right, same color when you draw 2. In that case now, so again, with replacement, or without replacement, first of all, without replacement, what happens? Without replacement, it means probability red first, red second, or red or blue first, blue second, because you're talking about the same color now. So that is probability R1, R2 plus probability B1, B2. So that means you have, so red is 3, right? So you have 3/5 times, now the same red now, after you have removed 1 red here, you have 2 red left and you have 2 blue. So everything is now 4. So initially it was 5, right? So now it's going to be 2/4 plus, so blue first, blue is 2. So you have 2/5. Without replacement, you have 4 left now. So, and you have 1 blue. So if you take 1 blue out of here, so you'll be having, so it's like you have 3R, 2 blue. So if you take 1 blue out, so you have 1 blue left. So everything is now still 4, but you have only 1 blue ball left. So that's 1/4. So that is 6/20 plus 2/20, and that is 8/20. And that is 4 in 8 is 2, 4 in 20 is 5. That's 0.4 without replacement. If you do that with replacement, so nothing, the total possibilities remain the same. So it's just like you check the ball and you return it. So everything up to this point is the same, but when it comes to this place now, you just have 3/5. Then you check the ball, you return it. So you always have the 5 balls. So that will now be, the red is still 3/5, because you return it. Then for blue, it's 2/5 times 2/5. And then all that is 9/25 plus 4/25. And that is 13 chances out of 25, which is that's 1300/4, right? Yeah, so it's like you have so the chances are less when there is replacement, because it's more like an infinite, so the balls are always the same. Okay, so this is how to do dependent events with or without replacement. You can even extend it to 3 items, like you want to pick 3 balls of different colors, and then you want to say what's the probability they are this. Okay, I've said different colors, or same color. So when it gets to 3, it can become really, really tedious, So, but I would like to stop here at this point in time. Thanks for following up to this point. If you have not subscribed, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. And of course, remember to always comment, like, and share so that more and more people can be part of these opportunities. See you next time. Bye.